one. Good morning, all of you. Am I audible?
Yes, ma'am.
Good morning, ma'am. Yes, ma'am.
Good morning. A lot of issue today from my end, so I was not able to start on time. So, okay, I'll just begin with, yeah. I've shared my Excel sheet with you. Is it visible?
Yes, ma'am.
Okay. Yeah. So, last lecture, we were doing complex integration. Okay. We'll continue with that. So, what we have over here is complex integration. Okay, so the first thing that we have seen over here is we have seen that we are trying to integrate a function f of z, a complex function, okay, with respect to this dz and along a curve t which will be given in the question. Okay, now what we have seen is sometimes the function is given in terms of x and y because our z is nothing but x plus iy. Okay, but finally we may be in. So our function may be having some real part u x y plus I times dxy. Okay, and similarly, this dz term here will be of this form dx plus I dy. Okay, so ultimately, what is happening here is we are having an expression y comma I times dxy. This is my function. This is to be integrated. Here we'll have dx plus I dy, and here we have the curve. Now see over here x and y, these two variables are appearing everywhere. Okay, and it's a single integral. Okay, so this is what we do not want to. It will be difficult for us to handle this one. So what is being done over here is that we will be replacing either y in terms of x or x in terms of y or x and y both in terms of another variable say t. So that ultimately what happens is the entire expression that we are having, it can be converted in terms of a single variable. That is the whole idea over here. Okay, so so let us take an example and try to do this. Okay. Question number one. We are trying to evaluate the integral 0 to 1 plus I x square plus iy dz, okay, along the path along the path number 1 y is equal to x, number 2 y is equal to x square. Okay, so these are the two paths that are given. So we are having this point. Suppose this is one real axis, this is the imaginary axis. Okay, so this is the point 1 plus I. Okay, so when we move along this line y is equal to x, it is this line and directly we reach this particular point. Okay, so now as I have said, either we can express x in terms of y or y in terms of x or both of them in terms of another variable. So any of these three things can be done here. Okay, so now let us think that we are going to replace the y variable by x. Let us do it this way. Okay, so in this case, what is my integrand? Therefore, my integrand x square plus iy will be equal to x square plus I. Okay, so my function has not changed. Okay, so this is the function which we will be integrating now. Okay, and why we could do this? Because the path of integration, the curve of integration is y is equal to x, so we could make this change here. Okay, now on the similar lines, the expression for dz, okay, dx plus I dy. Now again over here, we'll try to replace the y term that is appearing. So how do we do that? We are given that y is equal to x. Therefore, what will be dy? It will be same as dx. Therefore, this term turns out to be dx plus I times dx. So this is dx, or I'll write this here. This will be 1 plus I times d. Okay, having said so, hmm, having said so, now what next we need is next we need to just write down the limits. Okay, so now when we want to reach from this 0 to this particular point 1 plus I along the line y equal to x, along the line y equal to x. Okay, so what are the values for x? Actually, what we need now, see, we have decided to treat x as the variable. So everywhere wherever y is appearing, that has to be replaced. So now for this variable x, what is the variation? What is the variation for x? Now see this x goes from 0 to 1. Okay, so now over here to along this line to move from origin, that is 0 comma 0 to, or not 0 comma 0, let me call it as only 0. From 0 to 1 plus I, x x varies, varies from, from x equal to 0 to x equal to 1. Okay, so having said so, the entire integral that we have, integration from 0 to 1 plus I, and here we had x square square plus iy, this dz, this gets transferred to 0 to 1. Here we have got x square plus ix, and instead of now this dx, it will be this term coming 1 plus I dx. Okay. Now see, everywhere it is only just a single variable, so this we can handle. 1 plus I, this is a constant, I can take it outside the integral sign. 0 to 1 x square plus ix dx. Now the integration. So this turns out to be, I'll write it here, 1 plus I. What is the integration? X cube by 3 plus I x square by 2. Substitute the limits from 0 to 1. This will be 1 plus I. When we substitute the upper limit, it is 1 by 3 plus I by 2. Lower limit, when we substitute, it's all 0. So this is the expression. We have got two complex numbers. When we multiply them, we will get the answer. 1 by 3 plus I by 2. This is my answer. Okay. So even though there were two variables appearing here, we still can evaluate the integral by understanding that we are doing the integration along a particular path, along a particular curve. Okay. Now the second part to it, again the same integral is to be evaluated, but the path is different. Okay. The path is what is the path given? Y, wait, it's not working, it's hanged over. Yeah. Y, Y, what has happened? Y, is it visible to you people? Because when I am writing, I cannot see it.
No, ma'am.
I'm trying to write, but it's not visible. Okay, you people write it. Okay, so write y along the curve y is equal to x square. Okay, again we have this liberty. See here. So this is what I have said. So over here, check out. It's not writing. Only what has happened. And highlighter. So this expression, see here, either we can express x in terms of y or y in terms of x or x, y, both of them in terms of the third variable t. Okay, so any one of them can be taken over here. Now already the curve that is given is y is equal to x square. So which variable is expressed in terms of which variable? Over here, y is expressed in terms of the variable x. So again, we'll try to do the similar things. Okay. So what will be the x? So what will be the function in that case? What will be the function in that case? Yeah, now it started working. I don't know what has happened earlier. Okay. So now what we have got is for the second one. Let me, yeah, we have got y is equal to x square. Okay. So what will be the integrand? The integrand was x square plus I y. Okay, so this turns out to be x square. So we will replace y term now. Okay, it will be I times x square because y is x square. So this is the expression. So I can take out this x square common. It is 1 plus r. Okay. So now next. Yeah. So after this, what we have done is, after this, we'll simplify this expression dz. Okay, how do we simplify this? Dz is dx plus I d1. Okay, again over here, we want to simplify this dy term. How do we simplify this dy term? Check out, we are working along the curve y is equal to x square. Therefore, what will be dy? It will be 2x dx. And hence, the expression for dz turns out to be dx plus I times 2x dx. So what is this? 1 plus I times 2x times. Now see, even the integrand is in terms of one variable, and this dz term is also in terms of the one variable, that is x. And now we need the limits. Okay, how do we get the limits over here? We are, suppose this is the point 0 and this is the point 1 plus I. When we try to understand what this curve is, how do we do that? It is this parabola. Okay, now along the parabola, what we have got is y is equal to x square. Okay, so what is the variation for x? Okay, from where should we, what should be my initial value along this parabola? Along this parabola, what is the variation to move from to reach or to reach the point 1 plus I from the origin, we need to identify what is the variation for x. The variable x varies from where to where does it vary? What is the variation for this x part of it? What is the variation for x? Again, you just check. If I, in this expression, if I put x equal to 0, I'll be at origin. If I put x equal to 1, I will be at the point 1 comma 1. Okay, so x varies from 0 to 1. Okay, so we got the variation for this x also. Therefore, what is this expression?
How we got one?
Yeah, this for you again. See here, we want to move from this point, from this origin to this particular point 1 comma 1. Okay, just check. See, is it visible to you people? Yeah, now it's visible. Yeah, here, check out this expression. What is this value? This is 0. What is this value? This is 1. And these are actually the variations for the x coordinates. You just check this. These are your x values. And this part is the corresponding y coordinate. So if you put, just check out what is the variation for x now. Actually, the variation, the points, you have to just consider their x coordinate because we are taking x as my variable. Is this clear?
Yes, ma'am.
See here, I just have to identify what are the x coordinates to actually get what is the variation for this. Okay, so we got it from 0 to 1. Okay, now let us move ahead. So we are at this particular. So now what is the integration? The function was x square plus iy 0 to 1 plus I this dz. Now this gets simplified because of the curve that we have. It is from 0 to 1. Here what we have got is x square. See, this expression will come here. 1 plus I into the dx term is this 1 plus I times 2x. Okay, again check out, I'm getting a constant, so I'll move it outside. So 1 plus I dot, this is integration from 0 to 1 x square 1 plus I times 2x dx. How do I simplify this one? How do we simplify this expression now? So now, in order to simplify this, it is pretty simple. Integral 0 to 1. Let us multiply the x squared term inside. So plus I times 2x cubed dx. Okay, now evaluate the integral. 1 plus I. This will be integration of x square will be x cubed by 3 I times 2x raised to 3. What is the integration? 2x raised to 4 divided by 4, and these limits are from 0 to 1. So what we get is 1 plus I 1 by 3 plus 1 by 2r. Okay, now let us compare this answer with the previous one. So right now this is our expression, this is our answer. Okay, and yeah, here this is 1 plus I on. So are we getting the same answer? Yes, we are
Yes,
getting
ma'am.
the same answer. Yes. Okay. Many a times, but what happens is it may not be the case. Many a times we do not get the same answer. Okay. For example, if I take this particular thing, okay, let me attach a third case to it. Okay, third curve. We'll evaluate the same integral, but along a third curve. Okay, so suppose my curve is this one. Now, what my curve is from here, this origin, I want to reach to the same point. The point remains the same. Only the path that we are going to take is different now. Okay, so let me take a path. mm, let me see, which goes from here and then it goes vertically up. Okay, so first of all, it is moving, it is on the x-axis, the real axis. We are on the real axis and then we'll move upwards. Okay, so on the real axis we move from 0 to 1 and then 1 to 1 plus I. Is the path clear? What is the path of integration now? So this is the path of integration. Okay, so now it is a combination of now two curves. Okay, so in order to, so let me call this as the curve C1 and this as the curve C2, the straight line and the straight line. Okay, now how do I do the evaluation of this integral? So we want to evaluate the integration on the total curves. Okay, so one by one we'll evaluate. Okay, so this integration from 0 to 1 plus I, okay, of the curve x square plus iy Ez is nothing but along the curve C1, if I evaluate this, okay, and then I'll evaluate along the curve C2 and add both the things to get my total answer. Is this part clear? The curve that has been given in the third case, or if you want, I can tell you what the curve is, okay? So we can say C evaluate, let me write it in here, evaluate, evaluate integral 0 to 1 plus I x square plus iy dz along the curve along the curve along the curve C along the curve C um, which is which is on the real axis on the real axis from 0 to 1 and and then from 1 to 1 plus I vertically upwards. Yeah, parallel to vertically vertically upwards. That is what the curve is. Okay, so we have splitted it. Okay, this was my total curve C. We have split it into two parts, C1 and C2. So this is how we can write it here also. Okay, so now each of the integrals have to be evaluated separately. Okay, now along the curve C1, can you tell me what is the equation of this curve C1 that we have just now written? What will be the equation of the curve C1? We are on the real axis, so you need to tell me what is the equation of the real axis. Yeah, am I audible?
Y is equals to 1.
Is it y is equal to 1? Just think it over. You're quite close to it, but it is not y equal to 1. We are on the real axis. Real axis. Okay. I just wanted, actually these two lines, they are overlapping, but then I have not drawn them overlapping because I wanted to say that by a, and along this path only. Okay. Line is this one. This is my line. So can you tell me what is the equation of this one? This is my C. This dotted one. Okay, I've asked a really very difficult question and you people are not able to answer it. Okay, so I need to write down my real axis. Okay, the real axis is given by given by y is equal to 0. So when I say y equal to 0, it is the entire real axis. Okay, but then I don't want the entire real axis. I want what? I want to just start from 0 to 1. Okay, so what is the equation of the real axis? Y is equal to 0 and the variation for x. I don't need the entire part and I just need x from 0 to 1. Is this clear? The axis which we require is this and along with this condition. Otherwise, it will be the entire thing, okay? This is not C2. Therefore, this is the expression for C1. Okay, what is this? This is the curve C1. Okay, if that is the case, what will be my function now? X square plus I dy. What will be this? I have to put y equal to 0 now because the equation, the curve along which we are integrating, that is 0. Over there, for that particular curve, y is 0. This is nothing but x square and this part is gone now, it is 0. So this is the function. Now similarly, if y is equal to 0, next we need to simplify this dx step. So what will be dx? It will be dx, sorry, dz will be dx plus I dy. But then if y is equal to 0, what will be dy equal to 0? No, sorry, y equal to 0 will imply that dy is also equal to 0. So what will be this expression? Only dx will survive. Okay, so along this curve C1, see what we have got. Along this curve C, so what we have got is that integration along the curve C, along the curve C1. What we have, now this expression dz is nothing but integration x square dx, and what are the limits? See the limits we have just written here. Wait, I'll just move it up so that we can just see what the limits are. See here, we have written these limits. These are the limits that we have just now written. Okay, so we'll write it here. It will be from 0 to 1. This will be x cubed by 3, and the limits from 0 to 1, the answer will be 1 by 3. Okay, is this calculation clear now? On the similar lines, we'll evaluate the equation of the C2 curve. Okay, what was that C2? What is that C2 curve? Here we go. So now we want to evaluate this part. Okay, and how do we evaluate? Where is the C2? The C2 is this line. Okay, from x equal to 0, x equal to 1 to to the point 1 plus I. Over there we have to reach. So now you need to tell me what is the equation of this line. So by the way, this line is parallel to imaginary axis. So what will be the equation of that? What will be the equation of that? We are considering P2. P2 is the line joining 1 and 1 plus I. Okay, 1 and 1 plus I if I say. So what is the equation? It's the line parallel to x axis, sorry, y axis. So what is the equation? Who will tell me the equation? This is x equal to 1. Okay, now observe that when I say x equal to 1, suppose this is the point 1 and here is the point 1 plus I. So where is this line x equal to 1? It is this entire line. Okay, but we don't want the entire line over here. We want only this part of it, because this will be the curve C2. Okay, so we need to restrict. What can we restrict over here? The variation for y. Y goes from where to where? At this particular point y is 0 and at this particular point y is 1. Okay, so what do we get over here? Therefore C2 is given by x is equal to 1 and the variation for y is from 0 to 1. Actually, it is happening by it's just a coincidence that every time the variations that we are getting it is from 0 to 1. That may not be the case always. Okay, so having said this way, now we can simplify the expression. Okay, so we need to simplify the function. Okay, what will be the simplification over here? We will put these values. How do we put? So we will put x equal to 1. So when I put x equal to 1, so it will be 1 plus iy. Okay, now what about this one? Now we need to simplify this dz term. Dz is dx plus I dy. But then what we have is x is equal to 1. Therefore, what can we say about dx? What will be the derivative? X is equal to 1. What will be dx?
0.
0. So this turns out to be 0 plus I dy. That is only I dy. So we got the simplification of this dx term. Okay. Now we can do the evaluation. So therefore, the integration along the curve C2 for x square plus iy dz is equal to limits for y are 0 to 1. Okay, and this function is 1 plus iy. Dz term is I times dy. So I is constant, integration 0 to 1, 1 plus iy dy. So what is the integration? I is already there. Y plus I y square by 2, 0 to 1. I into 1 plus I by, okay, lower limit if I substitute, it is all 0. So this is the answer. Okay, so what is the total integration now? Integration from 1 to 1 plus I. This is what we require. Okay, along the curve C here. Along C1 and C2. If I add it, so I guess previously how much we got? Let's just roll it up. 1 by 3. And now we got this expression. This is 1 by 3 plus, here what we get is I minus I plus I square, so that will be minus 1 by 2. Okay, so we can compare this answer. So 1 by 3 minus 1 by 2. So this will be denominator is 6. This is 3. This is 2. We can compare this answer with the other answers. So now what we have got is, when we are taking this part, what is happening is, we are having this as the answer, the line integral. Okay. Now what has happened is, so now actually what can be concluded from this is that the line integral depends on the path that we have chosen. Okay. Same two points that we have, but the moment we change the path, we may get different values for the integral. So that is the conclusion over here. So you can write the conclusion here. So what is the conclusion? Therefore, the line integral depends on the path of integration. Okay, this is the conclusion. If we change the curves, we may land up in different values. It may be a coincidence that we are getting it as same, but generally this is the observation. Okay, now is there any special case where this dependency can be removed? That is our next question. Okay, so we have the answer over here that yes, there are some special cases where this dependency is not there. It means what? If I have a certain type of function, then whatever path we choose, we will be getting the integral to be a unique value. Okay, it will not be dependent on the path. Okay, and what is that condition? The condition is that if my function f of z, if this is, you remember in the last semester we have studied something special about some special type of functions over here. We have studied about analytic functions. Okay, so if my function is an analytic function, then what happens is, then the line integral does not depend on the path that we choose. Okay, for those who or another way of understanding this analytic function is that if my function f of z, it can be written completely in terms of z, say something like this. If this is the case, okay, there is no z bar coming over here. Okay, z bar is not coming over here. If that is the case, then the expression that we are getting is always an analytic function. Okay, so we have such functions, then the integrals, they do not depend on the path. Okay, I'll give you an example here. I ask you to evaluate integration of z raised to 3 plus 2z dz along the curve C, where C is. Okay, so no matter over here, whatever C I take, suppose I'm talking about, this is my origin, and I have some point here, say 1 plus 2i. So whether I go for, whether I go to this particular point along this curve, okay, or if I go along this curve, or if I go along with say, say this color, this path. Okay, so let me call these, name these curves. Suppose this is my C1, this is C2 curve. Okay, this is C3 curve going from here to here, and then going. All these paths, even though they are different, they will give me the same answer. Okay, that is what the understanding is. Okay, so when I know this fact, whatever curve they give me, this knowledge, see. So now I'll tell you, you go from here to here and then go to here. Okay, so what I'll do is I'll take a very straightforward path and I'll try to evaluate what the limits are. Is this clear what I'm trying to say? If see over here, we'll write down since z cube plus 2z. See now this expression. This function which we have written, it involves only the z term. Okay? There's no z bar coming over here. If that is the case, then what can we say about this function? This is analytic. Is analytic. Therefore, the integral of this function, is independent of the path. It is independent of the path. It depends only the initial and the final value. Okay, it depends only on the points that are being considered over here. Okay, is this much clear? It is independent of the path. Actually, it depends only on the depends only on the initial point and the final point. Okay, so how can we evaluate the integral? So now see over here, everything is in terms of only one variable, that is z. So I can very well do this integral. In that case, I can very well evaluate this integration from z cube to 2z. Suppose this is what I am going to evaluate. Okay, from the point 0 to 1 plus 2i. What I can do is, see everything is in terms of z, it's just a one variable. I can treat this as a single variable now. Okay, so what will be the integration? As it is this. The integration will be z raised to 4 divided by 4 plus 2 times z square by 2. Okay, and I can substitute the limits. Z is equal to 0 to 1 plus 2i. So this will be, what will be this equal to? 1 plus 2i raised to the power 4 divided by 4 plus 1 plus 2i raised to the power 2. It's done. So whether I take the curve C1 or I take C2 or I take C3, all of these different three curves will give me the same answer, which is this. Is this clear? Is this clear?
Ma'am, what about the previous one? It was not analytic or what?
It was not analytic because if I try to write that function in terms of z, we have used, yeah, here. So it is this function. Okay, how can I write it in terms of z? See, this is x square and this is y. Okay, so the problem is this function I cannot write it in terms of this thing z. Can I write it in terms of z? If I try to write z square, because यहाँ पर x square आया, तो z square का expression क्या हो जाएगा? x plus iy का square. Okay, so what will be this? It will be x square plus 2xyi minus plus I square y square. ये क्या हो जाएगा? x square minus y square plus 2xyi. तो अभी ये x square को मैं एडजस्ट करने के लिए जा रही हूँ, तो ये x square तो आ गया, लेकिन देन अदर टर्म्स आर आल्सो एक्सपेक्टेड. ये टर्म भी आना चाहिए था, वो तो आया ही नहीं है यहाँ पे. देयर इज नो y square का टर्म. देन हाउ डू आई ब्रिंग दैट y square into picture when that is not there? Okay, so this function is not analytic. और एक तरीका है, और एक तरीका है एनालिटिक चेक करने का. कैन somebody help me? How do we check analytic whether a function is analytic or not? Can somebody tell me how do we check whether a given function is analytic or not?
Derivative of
I'm talking
x.
about the function. Derivative of x. Quite close हो लेकिन थोड़ा सा फ्रेम गलत हुआ है. So we have got x square plus iy. So now
With
this is my
respect to x.
function. So I हाँ और so this is the real function plus I times dxy. ठीक है. अब ये फंक्शन का हम क्या करेंगे, रियल पार्ट आइडेंटिफाई कर लेंगे. तो रियल पार्ट क्या हो जाएगा, एक्स स्क्वायर है. ठीक है. मेरा स्क्रीन ना बहुत ब्लिंक हो, आई एम नॉट एबल टू, या नाउ. So my real part is u is equal to x square, and what is my imaginary part? V is nothing but y. You remember we. So what are the CR equations? We'll take the derivative of u. Come on, who will tell me? Derivative of u. What are the CR equations? Cauchy-Riemann equations.
D of x.
Dou u by dou x is equal to dou v by
dy.
dou y. Okay, so this condition is, this is the first equation, and the second one, dou u by dou y is equal to minus dou v by dou x. These are the two equations which should be satisfied. So here what is happening is now to be 2x. So this part is turning out to be 2x. This is 2x. Okay, this term is 2x, and what is this? Derivative of b with respect to y, it is 1. So they are not equal. Okay, when that function is analytic, that time the derivatives, these both the equations should be satisfied. Here in our, even the first equation is not getting satisfied, forget about analytic, then it means what? It will depend on the path that we are choosing. Whereas in the next case, that function is analytic. There are two ways of checking whether the function is analytic or not. First way is what? If the expression that is coming, it is completely in terms of only z. There is no z bar coming. ठीक है. अगर वो सिर्फ z के टर्म्स में है, then it will be definitely analytic. Okay. Otherwise, if the function is given in terms of x and y, then we can check for these CR equations, Cauchy-Riemann equations. If both the equations are satisfied, then we say that the function is analytic. अगर एक भी इक्वेशन नहीं सेटिस्फाई हो रहा है, एक इक्वेशन सेटिस्फाई हो रहा है और दूसरा नहीं हो रहा है, in that case this function is not analytic, and we cannot make any firm conclusions about the dependency of this particular thing. So if it is not analytic, it may depend on the path. Okay, analytic, then definitely it is independent of the path. तो आप end points लेके you can work out and you can simplify. ठीक है, यहाँ तक समझ में आया? Ajit, we will be seeing this case in some time. There in our syllabus. So what is our understanding right now? That if I am having if if we are evaluating an integral of a function which is analytic, then what we have over here is it does not depend on the path. It depends only on the end point. Okay? This integral is independent of the path.
Ma'am, your voice is slow, ma'am.
Okay, wait. Now is it audible?
Yeah, ma'am.
Huh. So this is independent of the path. Okay, it depends only on the end points. ठीक है? This is the first result that we have seen. Okay, now the extension of this particular thing. Okay, suppose my curve C which is given over here, it's a special curve. Okay, अभी मैंने क्या बोला कि I want to, suppose my C is, suppose I'll not draw this. So I have my C is somewhat like this. I am in this plane. This is the complex plane. Okay, and my C is such that I start from here. This is my initial point. I move. I can, yeah. I move along this and I'll come back to this particular point. Okay, it may not be a circle, it may not be a circle, but then anyway, if I move somewhat like this, ऐसे करके, but then finally I land at the same point. Okay, so if this is the case, okay, or actually now these curves they are called as the closed curves. What are these type of curves called? They are called as closed curves. Why they are called closed? You can see एक closed figure जैसा बन जाता है यहाँ पे. Okay. By the way, what do we mean by closed curve? If the initial point and the final point are the same, then the curves they are called as closed curve. Otherwise, curves होते कैसे हैं? ऐसे. What is this curve called? This is an open curve. Okay, इसका initial point different है और final point different है. So this is called as an open curve. Okay, and what do we mean by closed curve? If the initial and the final point are the same. ठीक है. अच्छा, इसके बाद भी we have some more things to study here. Some more category. Okay, now check out. Yeah, here. If I have a figure like this, if my curve is somewhat like this, okay, now see here, या फिर let me erase this. If my curve is like this, okay, now check out over here. If I try to compress this curve, ऐसे इसको, if I try to compress it, I'll try to push it inside. Okay, I can push this particular नहीं ये नहीं बोला था मुझे. Wait. Okay, before this one more thing. So now what about this particular point, this particular curve? See, I started from here and I ended over here. Okay, but then this phase what is happening is this is a closed curve. Is this a closed curve? It is starting and ending at the same point, so it is a closed curve. Okay, but then what has happened over here? This curve has cut itself. See here, what has happened is it has intersected itself. If that is the case, then we call this curve, okay, this is, it has cut. Okay, and if this case is not, if this is not the case, it means what? If my curve is not at all intersecting itself, then this is called as a simple closed curve. Okay, what about this one? This is not a simple closed curve. It is closed curve, but it is not simple. Why not simple? Because it is intersecting itself. Okay, now that is the case. Okay, so these are the different types of curves, and then we have something more over here. Hmm. Now, suppose my curve is somewhat like this. Okay, now if I want to shrink this particular curve inside, what will happen is, can I come to a single point? If I shrink everything inside, if I push everything inside, I can concentrate everything at a single point, whatever that point is. Okay, this is one case. So this is called as connected, and actually it is called as simply connected. Simply connected means what? If I shrink the entire region, I can be at a single point. Okay. Now, what do we mean by not simply connected? Now, see if I have this curve, this region. Okay, I have somewhat like this. I have somewhat like this, and here this is also a case. So see here. Suppose this is my region. Now, what about this particular region? Can I shrink it to a single point? If I try to move, I want to compress this from all the sides. Can I reach to a single point? Okay, just check out this one. I cannot compress this particular thing. Okay, so this is called as not simply connected. This is not simply connected. Simply connected. Okay, now we have a theorem which will relate to these particular figures, and the theorem what it says is, if we have a curve, if we have a simple closed curve in uh, in simply connected region, simply connected region, connected region. If we have a simple closed curve in a simply connected region, let me call that curve as C, simple closed curve C in the simply connected region, and we are trying to evaluate the integral f of z dz along this curve C, and also we have a condition on this f, that this is analytic. Okay, then then this is called as, then this value of the integral is always 0. Okay, this is actually called as the Cauchy integral theorem. So next session we will be working on this integral theorem, and we'll be evaluating the integrals. We'll see this again. How is this? So what we have seen is that this theorem actually gives us the value of the integral, and it says that the integral is always 0. But then what are the conditions satisfied over here? First of all, the function should be analytic, and we should have a simple, okay, simply closed curve, and it should be in a region which is not having such sort of holes जैसा कुछ vacancy जैसा यहाँ पे कुछ नहीं होना चाहिए. There should not be anything over here. Okay, blank spaces बीच में नहीं होना चाहिए. If that is the case, then what we get is that the value of the integral is 0. Okay, so this is called as the Cauchy integral theorem. Okay, so we will be doing this in the next Okay. By the way, today I don't have option to take your attendance. So you can do it softly. And just wait a second. Let me take and just on this. Aditya, please just click all the list, all the participants are list and just send me.
Yes, ma'am.
Go ahead. I'll put in the issue later. Just click the list and send me. Okay. Thank you all. Any doubts? Just wait for some time. Let him just click the list. Aditya, when you're done, you just let us know, okay?
Yes, ma'am. I'm done.
Okay. Thank you, all of you.